Okay, great. So for the final talk of the day, I think, we'll have Nika speak about some recent work on unifying algorithms for multi-calibration.
Thank you. Yeah, I'm really excited to be here to give this talk. Usually I give a talk that's more about the motivation of why we should care about certain things, but I feel like we've got a lot of motivation for why we should be caring about multi-calibration and fairness. So what I thought is there's very little kind of big picture as to why we should care about these things. And I'm approaching this talk as somewhat of a mini tutorial. It's a very general approach to designing algorithms for these settings that we've already agreed that we do care about. Multi-calibration, group fairness, and a number of other settings. So I know that nevertheless, I will have like 2 minutes of motivation. Just can't not do that. So we've definitely seen this like cartoon example multiple times, and also just kind of general motivation for the fact that while we're having more data, also this data is representing much more diverse groups of people, and we are using it in decision making for more and more diverse and also fine-grained types of guarantees that we are looking for. So this is a type of a cartoon example that we might have seen. We have different hospitals. Maybe they are actually representing different types of population. Some people with older age, some maybe minorities, some women. And we want to make sure that actually the types of decisions that we are making and for these different types of people are somewhat equally good in a way that we're not going to be making decisions that are completely high quality for some group and much worse for the other. And what this means is that we are going to be looking beyond the typical types of on average type guarantees that are so common in machine learning, because we do know that machine learning with on average guarantee works really well. What that means is that we are giving guarantees that don't hold for specific XYs, but for in expectation with high probability when XY is drawn from some distribution. But the issue is that while that's definitely good when our data is homogeneously like separated, like data centers, when it's actually people and organizational data, this is not the case anymore. And it's we've already seen examples, again, not even cartoon examples, where once you look within the subgroups, some subgroups are outperforming others. So what can we do if we want to go beyond this average? And what are the learning difficulties that we should be aware of? The difficulties we should be aware of are that different subgroups actually pose different types of challenge in terms of some have more data, some have less data, but also some data is just much more easily to classify. It just looks much more homogeneous within some groups, and other data looks much more messy. So what we need to do is to be able to learn these settings without really paying way above and beyond what we would have been paying for single distribution. Kind of like what Daniel was also talking about, trying to relate these things to also like what would have happened if it was just a single population. I'm going to give you 2 examples. The first one is something we've seen a lot, and the second one is somewhat closer again to what Daniel talked about. The first one is calibration. I know at this point, I don't need to introduce what calibration is at all. So this is making sure that your predictions are consistent. And we did see 2 versions of this. This, I feel like I'm making a caricature of this, but again, let's go with the toy version of thinking as calibration over existing data sets rather than online calibration in a way that Dean talked about, where it could be a rather weak guarantee whereby just guessing, the expected label, you're satisfying calibration guarantees, completely meaningless on any individual X. On the other hand, we have the per group version of calibration that we've been talking about throughout this workshop. This is the multi-calibration. There are different ways to write multi-calibration. The way I've written it here is with kind of expectation of label conditional on PX, kind of being close to, this should be kind of close to V being the predicted value, and S being subpopulations from set of subpopulations that were given to us. The second example I want to give, where again, we go from something that's classical and on average to something that's per group, is about agnostic learning or binary classification. Regression doesn't really matter, where now you're not necessarily learning an arbitrary predictor. You're given a function class and you're predicting based on that function class. This could be a 0-1 function. And you have a loss, which could be a binary classification or regression loss. again, we have the classical pack or agnostic setting that says that on average, I want to have a good error. So I want my expected error over a population to be close to epsilon or epsilon plus opt. And it's problematic, again, if you want to have it mean anything, because and something that has error of 5% could mean that on some 1/10 of the population has error of 50%. So that's, again, the problematic version of interpreting these classical results. What is the per group guarantee versions of this? Many different formalizations. When everything is pack learnable, all of them actually kind of go down to one version where we are thinking that you have multiple groups. Maybe they're represented by just different distributions. This, you can think about your distribution D condition on subsets of people, or you can just think about it as actual distributions D1 to dk. And then you're asking for a loss that's near optimal for every group. So this is, again, closer a little bit to what Daniel was talking about. I can give you more examples, but I think 2 is enough for a 30-minute talk. So what do we want out of this? I've shown 2 examples when we are going from single to multiple distributions or multiple objectives. And what we really want is to enable these learning processes that can satisfy multiple objectives and learn over multiple distributions, but from collectively fewer sample points and data. So what we want is to really make sure that sample complexity is not blowing up crazy. And while we have seen that this has a lot of relationship to fairness, I think there are 2 other things that we shouldn't forget. This is also a very classical robustness question. I'll give some citations, and also a data sharing and collaborative learning application. So beyond fairness, there's actually a lot of other applications we should be thinking about. What am I going to do in this talk? It's a mini/micro tutorial on statistical foundations of multi-objective learning. I'll try to hit 3 things. First one is, what is multi-objective learning as one unifying framework? And then how does multi-calibration look like in the multi-objective setting? How do you solve multi-objective settings? What are different ways of solving it? And what are optimal ways of solving it? And then hopefully I will have time to go beyond calibration and talk about multi-objective learning for other group fairness multi-distribution settings, again, touching more closely related to the last talk and some of the other stuff that we've seen. So what is multi-objective learning? I'm going to define the following approach to thinking about multiple groups in learning. Think about the setting I was talking about, multiple hospitals, each one has its own distribution. So we have a bunch of distributions, D1 to dk. And we can sample from these distributions. I can choose D2 and take 10 samples from it. We might also have different objective functions or loss functions, L1 to LR. What is L? Well, L could be anything really, but I think for the purpose of this talk, and especially because of multi-calibration, let's think about L that really relates to calibration. So while it could be like the binary loss, you could also kind of think about it more generally as, oh, maybe it's also something that looks kind of like prediction value as well being put into the loss. And then we're thinking about expected value of these losses. Then what we say is multi-objective learning is if you can simultaneously learn a single function f that is simultaneously good for every population and every objective. What does this mean? Well, one way to write this is to hope that there's indeed a function that would, for every j and every di, be less than epsilon. Because essentially, if I didn't have these 2 maxes, this LJDI would have been the pack learning setting or the calibration setting. But by adding multiple distributions and multiple objectives, I'm asking for the worst case guarantees to be really good, no matter which loss function and what distribution. This is uncovering a universally good model. It's not always guaranteed. Sometimes you just don't have a good function class, like maybe the function class you're allowed to be to take functions from are just not expressive enough. So more general way of expressing this is to bring the min-max value. So what does that do? You have something that you're guaranteeing, and you want this guarantee to be as good as possible compared to the best option you have in class. The best option is that min of H in H star, or min of H star in H. This is the best in class guarantee of this. I was planning to skip this, but just very briefly, let me say that while I wrote the min-max, there's a bunch of other ways of thinking about this problem, like specifically what Daniel actually showed, where you're thinking about generalization error, that is also enabled by this perspective, while it might not look obvious from the first sight. So this is just kind of saying that this does relate a little bit more generally. So don't get hung up on, maybe I don't want min to be here. Maybe I want it to be somewhere else. Okay. So what does multi-calibration look like in this setting? I have some loss functions in this setting. So multi-calibration better now talk about these losses. Like I have to actually create a function class, create a bunch of losses so that if you're satisfying multi-objective, you're satisfying multi-calibration. What does this look like? It's a simple exercise, but there's a point to this that becomes more clear because I think about this as a unifying perspective. So what is this exercise doing? It says that think about all predictors as your function class. So if it's binary predictions, your P of X is anywhere between 0 and 1. And now think about losses that are calibration style losses. What do these losses do? They take a subgroup S and they take a predicted value V. For a second, ignore sigma. What they say is that, well, what's a loss if you could say condition, but you could also say that if I just focus on the distribution of X's where I predicted almost V, so that's my predicted value, and X belong to the set S. So that's exactly calibration, and Y minus P of X is how far off you are. This sigma plus minus 1 is to say that if you overestimate or underestimate, both of them are bad. You should, you can't play with underestimating. So if you say this that way, then whenever you satisfy multi-objective learning, which is now this, you're actually going to be an S epsilon multi-calibrated predictor, okay? I wrote this as min-max because I want you to get used to seeing min-max, but this is actually 0 since the Bayes optimal classifier is perfectly calibrated, perfectly multi-calibrated. This is how you would write multi-calibration as multi-objective. There's another very common application. This is related to pack learning, where again, this is an example of multi-objective learning. Instead of thinking about too many objectives, you think about many different distributions. And then you ask the same thing. You're given a class H as opposed to constructing it. And then you're given a bunch of distributions. And what you want is to make sure that the worst case distributions loss is not much worse than the min-max.
So you said a quick caveat about sort of flipping min versus max in the minus term. But so is there? Yeah. So I'm just trying to make sure. So okay, for a fixed hypothesis class, wouldn't I want? So more like Daniel was saying, wouldn't it be max min? For the
depends what you're asking for. So if you do this, let's just say that they collapse if they share a Bayes optimal classifier. Let's first agree on that. If distributions share, okay. So now the trick is that most of the times that you get these really nice guarantees, what's happening is that there's a relationship between the Bayes optimal classifier. So what I can do is to write, for example, what Daniel wrote slightly differently and get this out of it, solve this and get that. So it's a little bit out of the scope of what I want to talk about in the next 15 minutes, but I can give some explicit citations for this and appendices where this comes up.
Let's make sure I'm understanding. Would you also get for the calibration? Is there a multi here?
Yeah.
Oh, it's for all the
S.
And would you get the same result? Would it be possible to just fix H to be the constant classifiers?
Constant classifiers.
Yeah,
as in you don't take X into account. This wouldn't be right anymore because you want to include at least your Bayes classifier, right?
I guess for the calibration loss, there was always a constant classifier that achieved 0 error.
It's offline.
I see. So you're thinking about an online sort of?
No, but for multi-calibration, you can't, right? Imagine if your S was each individual X, then truly you have to be the base optimal classifier. So
Guy, I think you're thinking about max min instead of.
Okay, maybe
min.
I don't. Oh,
Think
yeah.
about it this way.
I'm thinking about that.
this guy is if
Okay.
this base optimal. Okay, cool. Okay, so I said that I think about this as not just a pointless exercise, but as a unifying perspective. And I know we don't have a lot of time, but let me just put a whole bunch of works, and there's a bunch that doesn't include, like, just doesn't fit. You've seen already 3 of them. Multi-calibration, of course, you've seen. Rothblum, Yona, Daniel was just talking about it. I believe this work has been mentioned. I don't know how much we focused on it. But these 3 works, I think is good to know about, because this is about group distribution and robust optimization. That's the connection to robustness I was talking about. Connection to federated learning and agnostic learning, and connection to collaborative learning. Collaborative learning, actually, all these 3 become one, while these 3 slightly are different. The point here is to say that if you're going to focus on multi-objective rather than any single one of these settings, how would we approach solving them from a systematic perspective? And then can we generalize these approaches across the different types of, different bullet points, in fact. And for calibration in particular, which is going to be the main focus, what I find this perspective to really help is that it does improve some of the known guarantees, but I don't think that's the main point of this, at least not my main purpose for studying this in this way. But it's because we tend to know how to, in theory, we do better when we stand on the shoulders of giants. And the approaches that I'm going to at least give you are about very general, very well-studied forms of optimizations that hopefully we can kind of build up on and create a better understanding that generalizes to more difficult and complex tasks in multi-class, higher moments, and online and adaptive and XYZ type of multi-calibration. So how do we go from, I don't have a lot of time, but this is to say the point Daniel was saying. We want to solve the multi version of this, but let's not lose the sight of the single version of this, no matter what, both in terms of sample complexity, but also in terms of insights. I think it's really important not to lose that sight. So what is this kind of a more general way of solving multi-objective problems? The reason I focus on this min-max, even though not all of you love it, is because min-max is, oh, sorry, this shouldn't be here, it's just plus. Is a very general perspective. Once you have something that looks min-max, you know what's the first step to solving it. What is the first step? You think about it as a game between a minimizing agent and a maximizing agent. The minimizing guy is trying to reduce this loss over the choice of his action set, and the maximizing agent is maximizing the same loss over now her choice of actions. And what we know is that essentially what we're after is something that is satisfied by a notion of approximate min-max equilibrium. And forget about exactly what this means. The point is that this is related to a literature on game theory that's very well studied. And then how do we actually go about finding these equilibria? There are very generic ways of finding them. And essentially they boil down to making sure that one of your players is playing a no regret algorithm, while the other one has a lot more freedom. Either they can do no regret, best response, they can do anything that's not super naive. So this kind of opens up at least 3 different types of dynamics, both doing no regret or one or the other guy doing the no regret. So I'm going to be talking about regret, and I know I'm not the first person, but I want to know who here was familiar with regret before coming to the workshop this week. Perfect. So I don't have to go into a lot of details, but I will still just do the very minimal just to prime you to think about it in a certain way. I talked about best response and no regret. Let's clarify what I mean. Best response means that per time step, you're actually choosing something that was optimal for that time step, okay? No regret means that over many time steps, the choices that you made were near optimal, kind of in hindsight compared to the fixed option, no matter what the other player played. So what no regret for multi-calibration loss that I wrote down looks like for the minimizing player, this is the guy who's learning the predictor. He has no regret if he learns P1, P2, PT in an online way, given kind of the adversarial choices over which subgroup, which predicted value, and over versus underestimation. The loss, the calibration loss, now the multi-calibration loss, is very small. This is again, I wrote it as min, but this is again 0 if P was base. So this is saying that no matter what populations popped up, on average, you did quite well in terms of your multi-calibration loss. The maximizing player is the adversarial person who is picking the subpopulations, the predicted values, and over and underestimation. And he has no regret if he's essentially maximizing that loss, maybe minus a tiny bit. So what we do know about these things, and we've known them for decades, is that first of all, generic no regret algorithms exist. They exist in the sense that they're root T log of the number of actions available to you. And that how quickly we get to the solution concept, that min-max that I was talking about, is really a function of how quickly these two regrets shrink. So the faster they shrink, the better it is. Okay, what are some unique challenges to multi-calibration now? Well, one main challenge is that in general, we don't see distribution D fully. We can just sample from it. In general, no regret algorithms need to know what loss they're playing with. So we need to make sure that we can play no regret without taking too many samples. This affects the minimizing player in two ways. He might do best response, which means that we need to compute a predictor that's calibrated for whatever choice that came up, but without too many samples. It also affects the no regret version of this the same way. Again, we don't want to take too many samples, but there are some other things that also become important, in particular that whether PT itself has to be randomized or could it be deterministic. And that's because at the end of the day, for calibration, we would love to have something that's a deterministic predictor rather than a random predictor. Random predictors, calibration, they don't go very well together. For maximizing player, a similar kind of challenge exists. Can we do this without too many samples? And this is the ideal part, which is the dynamics that I technically showed you is taking time average predictor. So technically it's randomized. We need to make sure we can extract deterministic things out of it. These are three different types of challenges. The minimizing guy, the learner, the maximizing guy, and determinism. I'm going to mostly focus on this because if you figure out how to do this, the other two actually somewhat come naturally. So I'm going to talk about how you can make sure that you have a calibrated best response and no regret. And I'll really go to tiny bit of detail. The first thing is that the best response is something that was figured out a while ago. In fact, you can use some of the work from Dean's work and or if you want Sergio's perspective on this, that says that you could actually compute. If I give you a distribution over the loss, like the subgroup and the predicted value and all of that, you could, without looking at the distribution, actually have something that's multi-calibrated. So this is a point-wise guarantee. And intuitively, the reason this is something you could do is actually very similar to the reason that you could calibrate in an online fashion for an adaptive adversary. So pretty related. The second thing that I want to actually better understand is a no regret version of this. The no regret version says that for an adversarial sequence of L's, you could construct this predictor PT that has three properties. First, it's deterministic. The top one couldn't be deterministic. Second, it takes no samples from D, just like the top one. Third, its regret is independent of X, importantly, but it has a very particular form, square root of T, log of the number of labels. And at a very high level, I'm making a bigger claim. In fact, my claim is that take any no regret algorithm that can handle K number of actions. We have generic ones, hedge, whatever you want to call it. Then such an algorithm will give you a deterministic online calibrated predictor. And by calibrated, I mean with respect to the way I defined the no regret version in the last slide. Why is this the case? In some sense, what you're doing is that for each X, you ignore the fact that X's are different and you treat that X individually and interpret this predictor as itself a distribution over K actions. Okay, so what this means is that it's as if PT itself, a no regret algorithm, it's putting this a distribution over K things. Now, each of these actions has a very particular form of loss. And that loss, for example, in binary prediction, if I think about PT as the probability of predicting action 1 versus action 0, then the prediction loss is going to be the calibration loss the way I defined it. Okay, it's for whatever VT and ST and sigma T that the adversary picked. The adversary is picking these losses. If you set it this way, what happens is that the expected calibration loss of each X is the expected regret, is the expected prediction loss. And therefore regret becomes from prediction, like on K actions, becomes regret in this. So this is very general for any no regret algorithm. So what does this help us with? It gives us two dynamics. I can do the best response dynamic. This is not the ideal dynamic, but let's see what it looks like. The maximizing player is going to be the no regret guy, and his regret is not that bad, you know. The minimizing player is going to be the best response. This is the one I was saying that it's randomized, but you don't take a single sample. The maximizing player is going to need some samples to estimate. Imagine that it's taking a single sample. Then what happens is that we can show that the randomized predictor that's uniform over P1 to PT is going to be S epsilon multi-calibrated after these many time steps, which is exactly the inversion of the regret that I was talking about. What's bad about this? The fact that it's a non-deterministic predictor, but it's good because it's fast. Let me switch who's playing no regret and who's playing best response, because now I can do that. I have both. Let's say the maximizing player is picking best response to whatever the minimizing player did. The minimizing player is doing no regret. I think I didn't write that. Yeah. The minimizing player is doing deterministic no regret without sampling. Then we know that the randomized predictor is going to be doing well. But in fact, we know something more. The randomized predictor is doing well. It means that on average, one of these PTs is doing well. And since each one of them was deterministic, there is indeed a deterministic one in this set that I learned. That's a good predictor. It's an S epsilon multi-calibrated predictor. So this gives a deterministic and fast convergence. Let me say that this is the example you saw from Michael's talk yesterday. And you can kind of interpret it in the way that I wrote. This is doing the best response. In fact, this is a weak best response. We could deal with weak best response rather than thinking about the adversary doing exact optimization. And this is a very particular no regret algorithm. This is a gradient descent, but you could actually replace it with any other no regret algorithm. So why embrace the no regret dynamics? Well, the benefits of using this multi-objective thing is that I said it unifies and simplifies, but it also matches and improve existing results. So for example, let me see which ones I included. For K class calibration, rather than just two classes, the classical bound used to be polynomial in K. You can get logarithmic in K if you replace gradient descent with like exponentiated gradient is a bit hedged. You could also just simplify and improve a bunch of other results. I don't have time to go into them. But it also allows you to go beyond multi-calibration the way it's been studied. There's a bunch of other variants that are a little bit understudied. Some of them have been studied to some degree. Agnostic multi-calibration, where the base classifier is not consistent across different classes. Online multi-calibration, this extends to it, but without determinism. Adaptive calibration, or even just going beyond calibration for other group fairness. I don't have time to go on that. I'm just going to say that this version, the multi-distribution learning, is one that if you try to solve, neither of the two dynamics I gave you is the right dynamic to solve, actually. So what you would have to do is a totally different dynamic, which is the third one. And the third one says that instead of doing no regret versus best response, both players should play no regret. And if you do that, you can improve a lot of known bounds in multi-group learning, group DRO, multi-group fairness, collaborative learning, and XYZ. Okay, unfortunately, I don't have that much time, but I'm happy to take questions.
Any questions at this point? Okay, great. Let's thank Nika again. Omer will take over. Yeah. My work here is done.